We are going to get a quick review of functions. The definition of a function is given here. It's a rule that assigns to each element x in the domain exactly one element f of x in the range. Now you're used to seeing a y as the output, but in AP Calculus we'll use the notation f of x quite frequently. Please remember that the independent variable is the variable represented by the domain members, and dependent would be the range members. So here I have a graph of f of x, a sample function, and notice if I locate a value in the domain x, it has exactly one corresponding y value in the range, which we denote as f of x. So the inputs are the domain. They are represented by the independent variable, and we have f of x, which are the range members. Okay, one feature of graphs that you're going to have to work with is where is the graph increasing and where is it decreasing. So in pre-calculus, this becomes a discussion of how to represent your answer to the question. I want to tell you right away that where a graph is increasing and decreasing is represented by an interval, and what we're going to do in AP Calculus is write that interval as a closed interval. So I've marked the location A on the graph, and you'll notice from 0 to A this function is decreasing. So you would respond to that question with a closed interval. So from 0 to A the function is decreasing. You might also say, whoa, there's another place. Starting here and ending here, the function is also decreasing. Well, I'll call this location B and the end of our domain C, so that also on the interval from B to C, we have the function decreasing. In terms of increasing, again, just use a closed interval, and that would be from A to B, representing the interval over which the function increases. Okay, another feature of graphs, when we look at graphs, is we could perform a vertical line test. The vertical line test is where we could draw a vertical line anywhere in the interval that is the domain, and we would only cross the curve in one point. So if our relation is actually a function, then the vertical line test says we'll cross that function graph in only one point. You need to know that AP Calculus is the study of functions in 4 formats. So our book calls this the rule of 4. Verbally, you'll be given information and need to translate it into function form. You'll be given information numerically, which means we'll get a table of inputs and outputs. Visually, which we just looked at, a graph, so that is obvious. And then algebraically would be the equation or the model for a function. So what I'd like to do is look at something numerically, for instance. So I'm going to set up a table. X is my input, f of x is my output, and I think I'll use the function natural log of x. So the input for the function, I'll give 1 as an input. So the natural log of 1 would be 0. That's your output. And then I will choose e. So the natural log of e is 1. And then I'll choose 3. So the natural log of 3 is the natural log of 3, which I could represent with a decimal. But the idea is that you would be given the function numerically. Sometimes you'll only be given the table and you won't have a model. And then algebraically is this right here, the formula for the function. So you'll be given questions They're like the same question, but the given information will change. So you might be given this equation, or you might be given a table and be asked the same questions. So we'll get used to that. And then the last thing I want to say about functions is it really helps if you know what an even function is and what an odd function is. It'll make your work easier. So an even function is said to be where if you input the opposite of x into the function, you will get the same value as entering f of x. Now this takes on a certain feature when you look at the graph. X squared is one of those even functions. So here is a quick sketch of x squared. X squared is an even function, and you can tell that also graphically because there's symmetry with the y-axis. Another common function that's even is cosine. So here's cosine. I'm going to sketch that in. Cosine is also symmetric with respect to the y-axis. Now an odd function, if you enter the opposite of x into the function, your output will be the opposite of the function itself. This takes on symmetry with respect to the origin. And one of the most popular odd functions we have is the cube root function. So here's a cube root function sketched in rather quickly. You'll notice that there's origin symmetry, which means if I pick up the first quadrant and rotate it 180 degrees, I will end up with exactly what is in the third quadrant. That is also a composition of reflections. So you could reflect the first quadrant into the second, and then reflect the second quadrant into the third, and you would get the same image. So that is a discussion of what it means to be symmetric to the origin. The other very famous function that is odd is the sine function. You have to know what these graphs look like. I'm just sketching them from memory, and you need to be able to do that as well. So those are two functions that we have that are odd. The piecewise and step functions are going to show up in our work quite a bit, so I want to remind you of them. F of x equals, and then it'll be given to you in pieces. So like x plus 2, where x is less than 1. And then follow the formula x squared, where x is greater than or equal to 1. So here's an example of a piecewise function. So I'm going to focus on 1 as the input. So that's right here, that's 1. And it says in this piecewise function that before you get to 1, so to the left of 1, you follow the rule x plus 2. So it's not equal to 1 though. You won't have the graph of x plus 2 have an output at 1. If I did, it would happen at 1 plus 2, which is 3. But it's not going to happen there. When x is 0, I'll get 2. When x is negative 1, I'll get 1. So this is the piece of the function that's going to be graphed for x less than 1. Now, when you get to x is equal to 1, you have to follow the x squared rule. So when x equals 1, 1 squared is 1, and that will equal 1. And then after that, I'm following a parabola shape now. So at 2, I'll get 4, and then it's going to curve up from there. Okay, so that would be the graph of a sample of a piecewise function. The absolute value function is one of these piecewise functions. The definition of absolute value is that absolute value of x equals the opposite of x when x is less than 0. And then the absolute value of x equals x itself when x is greater than or equal to 0. So it's unchanged when x is greater than or equal to 0. The absolute value function is going to look like the shape of a V. So when x is actually 0, I'm at 0. So I get to 0.00. But everything to the right is going to be on the line y equals x. And then everything to the left of 0 is going to be on the line y equals opposite of x, because we're taking the opposite of x when we are less than 0. Step functions are also piecewise defined. The greatest integer function is a type of step function. I have written the definition of the greatest integer function if you've never had to learn this before. The output of this special function is the greatest integer less than or equal to the corresponding input. So it does a rounding of sorts. It rounds down to the nearest integer, and it's denoted with this symbol. So sometimes the brackets are just brackets, but most of the time it's like there's a double bracket here. And look at that in terms of a table. So we have our input and then we have our output. I'll write it like that. So I think I'm going to skip a couple places in the table just to examine numbers bigger than 0 first. So if I start with the number 1, it rounds down to the nearest integer. So we want the greatest integer less than or equal to the corresponding input. So I would get 1. But what if I put 0.5 in? It rounds down to the nearest integer. So greatest integer less than or equal. So the greatest integer less than 0.5 is 0. And then if I had done 0.1, I would still get a 0. So you see, when I'm at 0, I get 0. So 0, 0. And then when I get up to 1, it jumps to 1. So all the numbers between 0 and 1 are going to be graphed at 0 until you get to 1. And then when you go beyond 1, so let's say we do 1.5, what is the greatest integer less than or equal to 1.5? That would be 1. So everything between 1 and 2 is going to graph up at 1, except as soon as you hit 2, it jumps up. So it jumps up to 2. And then everything from 2 to 3 graphs at 2 because you're rounding down until you get to 3. And then at 3, we're up at 3, so we get to 4. This gets a little interesting when you are looking at negative values. So if you are at negative 0.5, if you're right here, the greatest integer less than or equal to that is negative 1. So this is going to graph down at negative 1. So you could see the pattern in the step already, so that's probably not too bad to conclude. Now you can see why they call it a step function. It looks like you have steps. And these functions are used frequently in real life today with billing of different commodities, such as your cell phone bill and how many gigabytes you use and for data and that type of thing. Okay, that ends our introduction to functions.